based on our graph. So networks are generally a general language for describing all the complex system of interacting entities. So it's actually mainly we are representing complex data by using this graph, and also by using new technologies are also similar one would can expect based on this network. And it's also shared among different fields, that is based on computer science, social sciences also, and it's also available to biomedical, health and medical, and also it's maybe applicable to social networking, social media and drug design. So in my concept, what is actually a network representation learning? It's actually is also known as the network embedding. So that is network embedding refers to an approach of learning a low dimensional feature representation of nodes or links in a network. And this goal of this network embedding is has to preserve as much of information as possible, and also it can be applicable to node link prediction and node classification, etc. And the main goal of this graph representation learning is representing the nodes or links in a networks into a low dimensional continuous representation, and it can be applicable, and there can be allowed many machine learning classification tasks can be done. That is, we can done a node classification, link prediction, and network visualization. And what is actually a network embedding? That is we are representing a node into a low dimensional feature vectors, and these low dimensional feature vectors can be given as an input to a machine learning task, and also it can be used to decode the neighborhood of the nodes, and also we can apply several node labeling, and that is node classification or community structures. And the goal of this network embedding, that is, it has to support the network inference in vector space. That it has to maintain network properties, and also it is used to reflect the network structure, and it can be fit for a machine learning model. So the basic this network embedding can be given to a classical machine learning task, that is it is applicable to node classification, that is to predict the type of a given node, or that is we can predict, we can label, suppose predicting the most probable labels of a nodes in a network. So suppose in this case, suppose if our nodes D1 and D2 are known, and suppose if you want to predict what is D3 and D4, so for all that we are using this network embedding application. And also it can be applicable to link prediction also, that is suppose if two nodes are pair of nodes are connected together, are not connected together, and we can check whether that two nodes they're having edges connecting them in the future or not. It is it's an application to a social network, that is in order to identify the friends networks. And also the other main application for the ML task for this network embedding is identifying the community detection, that is which all communities are by using clustering method, we can identify which all communities are clustered together, and also used to identify the network similarities, and also in order to learn the graph generation also. And the different network embedding methods are there are different models for network embedding, and the main category constitute about matrix factorization, random walks, and deep architecture. That is what is actually this matrix factorization. That is, it is a form of representing the connection between the nodes in the form of a matrix. That is factorizing the matrix and then after that it is factorizes in order to obtain the embedding. So graph rep is a representation of this according to this matrix factorization. And next is random walk, that is sampled through a random walks along the network, and then it is applied for ICMICDS model. Then after we are applying embedding method. The deep work and not to work is an example for random walk methods. And next is deep architecture, that is viewing the network as a computational graph, and then we have to train the entire model to an instant faction. Graphic is an example. And then what is actually this random walk? So consider this is a graph. Suppose we have to starting from a node 1. Suppose we have a random walk to 2, or we can have a random walk to 4. So that is actually a random walk, that is visiting each of the neighboring nodes. Suppose if you want to go to 2, then it has to go to next. It has a chance that it can go to 4, and also it has to go to 5. So suppose if you are going to 5, then 1 to 2, then 5 to 6, then 6 to 7, 7 to 8, 8 to 3, then to 4. That is actually a random visit. So this process is also actually known as a random walk. And next, our one of our embedding method is not to work. So this not to work is a random walk based node embedding method. And also that is the neighborhood of the graph is sampled through this random walk. So in case of not to work is applicable to node classification, link prediction, etc. That is actually we are having a series of random walks around the nodes in a network, and we have by using those sequences we are applying to an embedding algorithm. So there is a, suppose we are considering a graph, and then we have a random walk along the graph, and then it is applied to a scriptgram model, and we have to select which one should be the next node, etc. And then it is applied to embedding. And in case of not to work, we are having 4 parameters are the number of walks, walk length, a return hyperparameter P, and a input hyperparameter Q. And here basically in case of not to work, we are basically uses two search and structures, that is birth first search and depth first search. That is in case of a birth first search, it has to capture the local neighborhood and then find the embeddings. And in case of a depth first search, it basically focus on identifying the communities. That is not only for the nearest neighborhood, it is also for the other nodes that are connected to the communities also. So basically, basically we are using this network mainly for 2 main purposes: network roles and identifying the communities. That is structural equivalence and homophily. Basically, 2 strategies are the DFS and BFS. So this network actually generate it's actually a numerical representation. That is, it's actually used to represent maybe if nodes are the different person, and if the suppose we have to check whether there is a connection occur between the 2 nodes or that. So it is actually an embedding method that transforms the graphs into the corresponding numerical representation. So in this case also we are considering 2 random walks are the first order random walk and second order random walk. So the first order random walk is done by sampling nodes on the graph along the edges. That is, the nearest neighborhoods are actually taken. And in case of second order random walk, we are not only considering the current state, but also we are considering the previous state also. And the first order random walk, we have one hop transition along the network. That is, the nearest neighborhood are taken, the current states are actually taken. But in case of a second order random walk, we are considering also the previous nodes also we are considering. And the node to work, it's actually we are having a random walk along the networks, and then it is applied to scriptgram model. So the scriptgram model, we are considering it as a representation of a text sequence, and we are selecting as a form of a text sequence, and we have to select which should be the next one, and then it is given to a graph embedding process. So in case of a scriptgram model, suppose this is a source test, and we are selecting, suppose in this case this is actually a sentence, and we are suppose we are taking a word the, then the next should be the cube, the brown, the fox. Like that, we have to train the samples. And the next case, suppose we have to take a cube, then the training sample should be cube, the cube brown. Like that, we have to select. Here also, we have to select the random walk based on this scriptgram model, and then we are applying the embedding methods. So the basic classic strategy for this not to work is actually BFS and DFS. That is, in case of BFS, we are considering the nearest neighborhood. So consider a node U. The nearest neighborhood can be S1, S2, and S3 in case of BFS sampling. But in case of a DFS sampling, not only to U, we are from node U, we have to consider S4, then to S5, and then to S6. So this actually mainly used for considering that is for identifying the communities. So in case of a network with random walks, first we have to initialize, first we have to identify initial node, then look at the neighbors and select one as the next node, and then repeat the steps until the random walk should be equal to 1. And this is actually an algorithm for the network algorithm. Here also we have to consider a graph, and then we have to initialize the walk, and then we have to consider a random walk along the nodes, and then we have to apply the nearest neighborhood, we have to find out the nearest neighborhood, and then it is given to this network algorithm is actually given to an embedding method. So the next network embedding method is attribute to work. Here also we have to learn the node representation by performing linear or non-linear mapping of nodes or contents or attributes. That is, here we are considering the neighborhood also, that is nearest neighborhood are considered and they are clustered together. And this is actually based on, we are considering this nodes that are close together based on basically by using a structure similarity nodes are considered, and we have to perform a transformation function, and then we have to arrange the method. So here also it is used for learning high quality node representation, and it is basically we are clustering the nodes based on the capture, how to capture the structural information of the nodes, and then we have to find the transformation. Suppose this is the original attribute space, and then this is actually a network structure, that is the similar structured element nodes are combined together, and then they are connected together, and then hello.
Your time is over, so please continue.
Okay. And then we are applying the transformation function, and then here also we are applying mainly we are using the 3-layer neural networks, which actually it consists of input layer, hidden layer, and the output layer. And this attribute next is actually the graphage method. So this graphage method is also a low dimensional vector representation. And here mainly we are using an aggregate function. That is aggregate function is actually taken, and there is an input graph. Suppose this is input graph and there is a node A, and you have to take an aggregate function, and then you have to consider node B. Then from B we have to use aggregate function and then find out node A and C. From C we have to take F, E, and A. From A we have to take A and D. And next is a graph convolution network. It's actually similar to that of a convolution CNN network. And so actual operation is basically this graph convolution network is mainly used for feature extraction and classification problem. And also here we have to identify the nodes of the nearest neighborhood as actually find out. And also I have conducted experiments based on these four models based on two data sets, core data set and PubMed data set. And I have to obtain two tasks, other link prediction and visualization. And so these are my results, and this is my result. And based on the AUC value, I have to and according to my conclusion, I have obtained based on this link prediction and based on this visualization, and higher values have been given for this attribute to wet model. And then we have to consider two data sets are there, PubMed and correlation. This are also apply visualization also to the network. And so these are my selected references.
Any queries from the participants? Okay, so we shall move to the next presentation. C11, Gokul S. Jayakumar.
Yes, ma'am.
Okay, so please share the presentation.
Sure. Is it visible, ma'am?
Yes, it is visible. So your time starts now.
Yeah, thank you. A very good morning to one and all present here. I'm Gokulas Jayakumar, a scholar from the Department of Mathematics of Christ deemed to be University, Bangalore. I'm here today to present the research article, Perfection of Modular Product of Graphs, authored by myself and Dr. Sangeeta V. First, I'll go through the overview of the paper. It includes an introduction. I will just go through a slide with fundamental readings that led to the research results in our paper. We'll also go through some prerequisite graph classes and definitions that are required to understand the paper. The papers here, the second paper is a paper communicated by myself and Dr. Sangeeta V. We had defined induced cycle perfect graphs, which I'll be explaining soon. So to start with, we have perfect graphs. Burge has defined two types of perfect graphs. One is the chi perfection, and the other is perfection. In this, we have inspired from this topic alpha perfect graphs and introduced a concept called cycle perfect graphs by replacing clicks with cycles, clicks with induced cycles in our choice of graphs. So for alpha perfection, we have that graph be alpha perfect if the independence number is equal to the covering number for all induced subgraphs of a graph G. So the independence number is basically the number of vertices in a graph such that no two of them belong to the same click. And the covering number is the minimum number of clicks required to cover the vertex set of G. So here we are replacing clicks with induced cycles, and we get to cycle perfect graphs. So the new parameters are induced cycle independence set and induced cycle covering set. So the induced cycle independence number, or alpha C of G, is the cardinality, it is the maximum number of vertices in G such that no two of them belong to the same induced cycle. And C covering number, or cycle covering number, denoted by theta C of G, sorry, that's a typing error. Theta C of G is the minimum number of vertices in the graph G required to cover minimum number of induced cycle in the graph G required to cover the vertex set of G. So with these parameters in hand, we can define C perfect graphs. A graph G is said to be C perfect if alpha C of H equals theta C of H for all induced subgraphs H of G, where every vertex in H belongs to at least one cycle in H. Now, since we are considering cycles as the basic graphs, we are restricted to graphs. We are restricted to such graphs where every vertex belongs to at least one cycle. And that's property. This is an example of a cycle perfect graph. Here we can see that considering any vertex of degree 2 from the cycle Cn, if we consider one vertex from Cn, say this particular vertex, we won't be able to consider any other vertex from Cn because they share an induced cycle with Cn. So we can consider the next vertex that can be considered is this one from the degree 2 vertex from Cm, creating alpha C of G to be 2. And clearly, it can be identified that since this graph does not contain a induced Hamiltonian cycle, theta C would be greater than 1. And to be precise, Cn and Cm would cover the vertex set of G. So theta C can be given as 2. So, and all induced subgraphs satisfying property P in this particular graph are cycles, which are trivially C perfect. Therefore, the graph is C perfect. Now, moving on, we have an example of a graph which is not C perfect. Here, this particular graph, alpha would be 1 here, but theta is not 1 since it does not contain an induced Hamiltonian cycle. Yeah. Okay. Now we get into the definition of modular product. This is the definition of modular product. A graph G modular product G2 is a modular product of a graph G1 and G2 such that the vertex set is the Cartesian product of the two graphs G1 and G2. And second point is that considering any two vertices UV and XY in G1 cross G2, these two vertices are said to be adjacent if and only if U is distinct from X, V is distinct from Y, U is adjacent to X and V is adjacent to Y, or U is not adjacent to X and not adjacent to Y. Okay, so these are the definition of graph minors and subdivisions. An undirected graph G H is a minor of G if it can be formed from G by removing edges, removing vertices, or by contracting edges. And IS K23 free are graphs are induced subdivisions of K23 graphs, and a graph is said to be IS K23 free if it does not contain any subdivision of K23 and induced subgraph. Now these are the main results in our paper. If G is C perfect, then it is P4 modular product P3 free. So with the help of this one, we were able to characterize all path cross path. I mean path modular product path graphs. So modular product of two paths is C perfect if and only if both have exactly 3 vertices. That is, if n equals 3. If both the components are 3 p's, only then will a path graph modular product of two paths be C perfect. Further extended this to acyclic graphs, product of all acyclic graphs. If G1 and G2 are trees, then G1 modular product G2 is C perfect if and only if both G1 and G2 are isomorphic to P3. Now we extended this to cyclic graphs. G modular product P2 is C perfect if and only if G is C perfect with at most one. This is possible with the help of an existing result by Dr. Sampath Kumar. Duplicate graphs. So G modular product P2 would be isomorphic to duplicates. So with the help of that theorem, we were able to prove this. A graph G is C perfect if only if it is a P3 modular product Ci free for n greater than or equal to 3, and a Ci modular product Cj free greater than or equal to 3. With these lemmas and theorem, we're able to characterize modular product of two graphs. The modular product of two graphs G1 G2 is C perfect if and only if G1 is isomorphic to K2 and G2 is a C perfect graph with at most one induced cycle, or G1 and G2 are isomorphic to P3. And this is the generalization for n number of products. G equals G1 modular product, etc. Gn is C perfect if and only if there exists exactly one graph GI where I belongs to 1 to n, such that GI is a perfect graph with at most dot cycle, and GJ is equal to isomorphic to K2 for all the other J, where J not equal to I, or G1 n equals 2 and G1 cross G2 is G1 is isomorphic to G2 and it's isomorphic to a P3. These are my references. Thank you.
Thank you, Google. Any queries? We are moving to the next one. Sri Kumar KG.
Hello, madam. I am the second author, Jayagumar C. We have equal share in this, so I am going to present the topic.
Okay, sir. Okay.
Okay.
Yes, sir. It is visible, so your time starts now.
Okay. Can you see the slides, madam?
Yes, sir. It is visible.
Okay. Okay. To begin with, let me introduce myself. I am Jayagumar C, Assistant Professor of Mathematics in Gola Karnataka. I'm also doing part-time research under Dr. K. Manilal, Associate Professor, Department of Mathematics, University College. My topic is a study on topological indices of bipartite Nasser B type 1 graphs. For a fixed integers n greater than 1 and k greater than or equal to 1, we take bn plus 1 as a1, a2, a3, etc. an, where these ai's are real numbers, and we take b1 as the set of all k element subsets of bn plus 1, and where 1 less than or equal to k and up to n minus 1. Now we form a set phi of bn. Phi of bn is a set of all non-empty subsets of bn, and bn is described here. Bn consists of elements of the form plus or minus a1, plus or minus a2, etc. up to plus or minus an minus 1, and the last element is an. Here all ai's are positive real numbers. One more condition is there: a1 less than a2 up to less than an. At the same time, minus an is not an element of Bn. Now, we form a new set B dagger. The B dagger is formed by taking absolute values of elements in B. So here B is a member of phi of Bn, or B is a subset of phi of Bn. Now we associate a bipartite graph with partition V1 and V2. Here the adjacency is defined as the vertex A is adjacent to B if and only if A subset of B dagger or B subset of B dagger subset of A. This graph is called the bipartite Nasser B type K graph, and it is denoted as HBNK. In this paper, we derived Wiener index, peripheral Wiener index, and peripheral Hossier polynomial of HBN1. That is a case when K is equal to 1. In introduction, the author mentioned in reference 5 introduced HBNK as a generalization of SN balancing graph SMBN, mentioned in 6. It was established using the combinatorial structure of the balanced ternary number system, which is used in the Saturn computer built in Russia. We established some of the parameters, especially Wiener index, peripheral Wiener index, etc. We analyzed the peripheral Wiener polynomial also. Basic definitions. This first definition I have already mentioned in the abstract. Here I am going to discuss about HBN1, a special case when K is equal to 1. In HBNK, we take V1 as a set of all K element subsets of Bn plus 1. Here in HBN1, we take V1 as the set of all one element subsets, namely set A1, set A2 up to set AN. And we form the V2 as before. V2 is equal to phi of Bn minus V1. And also we take B dagger. Now we define a bipartite graph like this. A in V1 is adjacent to B if and only if A subset of B dagger. This particular type of graph has a special case for HB and K. It is known as bipartite Naser B type 1 graph. And next two definitions are used in the theorems to be followed. And then the definition of independence number and the domination number are also given here. Then define the various definitions such that Wiener index, hyper-Wiener index, then peripheral Hoshaya polynomial, and the peripheral Wiener index of the graph are given over here. And these definitions are used to find out the corresponding topological indices of our graph HBN1. Then we have also introduced a polynomial. Various works on this polynomial are going on now. We have associated, we have defined a polynomial using the elements of Bn we have already discussed. That is, the polynomial associated with Bn is an x raised to n minus 1 plus or minus an minus 1 x raised to n minus 2, etc. plus or minus ai. Work is going on in this direction also. Now, an example of HBN1 when n is equal to 2 and k is equal to 1 is given over here. We can see that this in V1 contains the bipartition. V1 contains the elements set A1 and set A2. V2 contains the elements set A1, A2 and set minus 1, A2. Now, V1 is adjacent to take A. I take A as set A1 and B as set minus A1, A2. Now, you can see that A is adjacent to B. The condition is A is subset of B dagger. And we take B as set minus 1, A2. B dagger is formed by taking the absolute values of elements in B, which means B dagger becomes set A1, A2. Now, clearly, A is a subset of B dagger. For the same reason, we say that A is adjacent to B. In the same manner, we can take another set A2. You can see that set A2 is adjacent to set A1, A2 using the same adjacency relation. So we have seen that it is a bipartite graph. I have also included here the case when HB41, that the graph is not drawn over here, but the bipartition is given. In the here, for the convenience, I take A1, A2, A3, A4 as 1, 2, 3, 4. And we can see that from V1, it contains singleton sets, and V2 contains sets of order 2, 3, and 4. So care should be taken to see that in every subset, the last element is positive. So I have formed V1 and V2 using the conditions I have already discussed. You can see that this bipartite Naser type B graph has 1 by 2 into 3 raised to n minus 1 vertices and n into 3 raised to n minus 1 edges for each n greater than or equal to 2. And also, we have obtained degree sequence. Here, degree sequence is defined in a special manner. We can see that the set V2 has degrees, has vertices of degrees 2, 3, etc. up to n, and V1. Every vertex in V1 has a degree given by 3 raised to n minus 1 minus 1. Moreover, V2 contains degree 2 NC2 vertices of degree 2, 2 square NC3 vertices of degree 3, and so on, and n vertices of degree 3 raised to n minus 1 is in V1. And algebraic properties of these graphs are being studied simultaneously in another paper, like vertex transitivity, edge transitivity, and the non-asymmetric properties. These are the main results. We calculated the vertex independence number, and also we discussed, we calculated the distances. The 4 distances are there, distance 1, 2, 3, and 4. We discussed various cases in which these distances are calculated. And also, we determine the domination number. For finding out the topological indices, number of unordered pairs having distances 1, 2, 3, and 4 are required. So we have calculated these also. So D1 UV means number of unordered pairs having distance 1. It is obtained as n into 3 raised to n minus 1 minus 1. Similarly, we calculated unordered pairs having distance 3 d3 uv, a distance 4. And also, we calculated unordered pairs having distance 2. And all these are used to find out the Wiener index, hyper-Wiener index, and Wiener index and hyper-Wiener index. Wiener index is calculated here. Moreover, hyper-Wiener index is calculated here. We can see that using the definition of these Wiener index, and Wiener index needs distance. We can see that Wiener index is a topological index. It is used in a chemical graph theory, and Wiener index is given to be sigma duv. So we require distance between pair of vertices. As we have calculated all possible distances, we have easily calculated Wiener index. Moreover, hyper-Wiener index is calculated using distance. So we, using the formula given over here, we calculated the hyper-Wiener index also. Then we calculated other things like we calculated the peripheral Wiener index and peripheral Wiener index, and then we calculated the Hosaia polynomial, and all these are calculated using the eccentricity. We have calculated the eccentricity to be 3, 2, and 4. Using these eccentricities, we calculated the Hosaia polynomial, and also we calculated the peripheral Wiener index. And we are going to conclude. In this paper, we determine the vertex independence number, vertex covering number, domination number, distances, eccentricity, Wiener index, hyper-Wiener index, peripheral Wiener index, and peripheral Hosaia polynomial of the graph. There is a lot of scope for further work. It can be applied in fields such as LDPC codes, normal coding using graph automorphisms, the mathematical modeling language called PetriNet, and quantum state transfer. These are the references. Thank you. Thank you.
Okay, so thank you. Any queries? Okay, so we shall move to the next presentation. Suja and Thomas.
Yes, I'm here.
Yes, you are audible. Please share your presentation. Jamal.
Hello, is my screen visible to you?
No, ma'am.
No.
When you are visible, but your screen has not been shared.
Okay. Okay, is my screen visible now?
Yes, ma'am, it is visible.
Oh, okay.
Thanks, Johnson.
A very good noon to all. I'm Sujan Thomas from College of Engineering, Chapter. My research work is under the guidance of Dr. Vinod Kumar, Professor Rajagiri School of Engineering and Technology. The title of the paper is on maps with dense periodic points and set of periods Z plus. The objective is to observe whether there is implication between per of F closure is equal to X and P of F is equal to Z plus. Define a periodically rich maps and study periodically rich maps on interval, circle, compact manifold, and function space. In dynamic system, we study the behavior of a system over a period of time. We consider a discrete dynamic system except where X is a topological space and F a continuous function defined on X. And the behavior of a point X in the space under repeated iterations of continuous function F is analyzed. First, let me give some basic definitions and notations. A point X in the space is called a fixed point of if f of X is equal to X. Is called a periodic point if there exists an n in Z plus such that Fn of X is equal to X, and the smallest n is called the period of n. And set of periodic points with period n we denoted by per n of F, and set of periods of F is denoted by P of F. And the set of all periodic points is the union of all per n of F. And the orbit of a point in the space is the sequence X, f of X, f square of X, f cube of X, etc. and is denoted by O f of X. And if X is a periodic point, orbit is finite. On interval, we say that the orbit is increasing if O f of X is an increasing sequence. Given two open sets U and V in the space, if there exists an n in Z plus such that Fn of U intersection V is non-empty, then F is said to be transitive. A subset A of X is said to be dense in X if A closure is X itself. In the theory of dynamic system, per of F and P of F help us to understand the behavior of the system. In general, set of periodic points can be empty, a finite set, a countable set, or an uncountable set. Set of periods can also be empty, a finite or infinite subset of Z plus. Now, the question is a dense periodic points imply P of F is equal to Z plus and vice versa. So let us consider some examples on intervals. For the map whose graph is shown here, here P of F is not Z plus, but per of F is closure is 0, 1. Now for the map whose graph is shown here, per F of F closure is not X, but P of F is equal to Z plus. For the 10th map, both the conditions satisfies per F closure is equal to X and P of F is equal to Z plus. And for the map defined by F of X is equal to X square on 0, 1, there are no periodic points. It has only fixed point 0 and 1. So neither of the conditions are satisfied here. So we define a periodically rich map as a map with both P of F is equal to Z plus and per of F closure is equal to X. Set of periodically rich maps defined on X is denoted by PR of X. We say that X admits periodically rich maps if PR of X is not empty. Clearly, PR of I is not empty because a 10th map is there. On interval, periodically rich map on I could be divided into two classes. The first is those transitive maps having a period for point with increasing orbit, and the second is those transitive map such that f of X is equal to X, and for some X in 0, 1 and f of 1 is equal to 1, and for every closed interval J a subset of I, f of J is not a subset of J. Both the class have a transitive map, so a transitivity implies a dense periodicity on interval. So what remains to prove us P of F is equal to Z plus. For the class 1, we could show a presence of period 3 point. Then by the famous Sharkovsky's theorem, the P of F is equal to Z plus. And for the class 2 maps, we use a lemma A less than B less than C such that f of A is equal to A, f of C is less than or equal to A, f of B greater than or equal to C, then P of F is equal to Z plus. And this lemma is proved using a standard result by Lior in the paper period 3 implies chaos. Now, considering the maps on circles, there are few direct consequences of result in the literature. One is if mod degree of f is greater than or equal to 2 and f has period 2 point, then f is periodically rich. And the other one is if f is transitive and f has periodic point of period 1, 2, 3, then f is periodically rich. Now, transitivity is not a necessary condition for a map to be in PR of x. For example, if you consider a map whose graph is shown here, this is not transitive because the iterates of f in n plus 1 will remain in that block itself. It will not go out. And but both the conditions P of f is equal to z plus and per of f closure is equal to r satisfies here. Now, how big is this PR of I on C of I? And C of I is the space of a continuous functions defined on I, and P of I is the set of all maps which are transitive. And a PR of I is those set of maps which has dense set of periodic points, and P of I is those set of maps which P of f is equal to z plus. Now, P of I is a subset of P of per of I, and P of I intersection of P of I is non-empty. Now, we can show that this P of I is dense in C of I. So for that, what we do was we construct G in P of I corresponding to F in P of I such that the norm of F minus G is less than epsilon. The construction is in such a way that we insert a map at the fixed point, a map which is homeomorphic to 10 map at C plus 2 theta, and then in C plus 2 theta, C plus 3 theta, we insert a line segment. Then like this, and this will be such that mod f minus e will be less than epsilon. And if the fixed point is at 1, then the constructions are like this. And so we have the corollaries. At each point of f, we can construct such g's, and therefore the cardinality of such g's is equal to the number of fixed points of f. Coming to the maps on manifolds, the result is every compact manifold of dimension greater than or equal to 1 admits periodically rich maps. To prove the theorem, we use two lemmas. So one is a lemma by Neteki and the other is lemma by Arts. The first lemma is proved, that is, for every epsilon greater than 0, there exists a continuous map f from R to R such that f of x is equal to x for all x not in minus epsilon epsilon, and mod f of x minus x less than epsilon, and f of x is equal to z plus. Then an analogous result of this lemma is here, that is, let a VR of 0 be the n-dimensional ball centered at origin and having result are greater than 0. And for each epsilon greater than 0, there exists a G from VR of 0 to VR of 0 such that norm of G of x minus x is less than epsilon, and then P of G is equal to Z plus. And this lemma is used to prove the theorem, and the lemma by Arts is also used in the theorem. Now, the periodically rich maps on function space, and we consider a map on the space of our continuous functions on 0 infinity with supremum metric. We could show that there exist periodically rich maps on C0 infinity. We define phi on C0 infinity as phi of G of t is equal to 2 G of t plus 1 for G belonging to C0 infinity. And then we could show that phi is periodically rich. So the conclusion is every compact manifold of dimension greater than or equal to 1 admits periodically rich maps, and the function space C0 infinity also admits periodically rich maps. These are some of the references. Thank you. A word of thanks to the organizers of ICMICDS-22 and the management of the Rajagiri School of Engineering and Technology for giving me an opportunity to touch on the paper.
Okay, thank you, ma'am. Any queries from the participants? We are moving to the next presentation. Ms. Bindu VA.
Hello.
Yes, ma'am. You can share your presentation.
Okay. Hello. Can you see my?
Yes, your screen has been shared. Your time starts now.
Good morning. I am Bindu VA, a scholar in National College, Trichy, under the guidance of Dr. Manju Somana. My paper is on the exponential Diaphantine equation related to power of cluster primes. In the introduction, the prime time mathematics explores prime numbers which lie at the heart of number theory. Some prime cluster together and some are widely spread, while primes go on forever. The sieve of Eratosthenes is an ancient method for identifying primes by iteratively marking the multiples of each prime as not prime. Every integer greater than 1 is either a prime number or can be written as a product of primes. An odd prime P is called a cluster prime if every positive integer less than P minus 2 can be written as difference of two primes, that is Q minus Q dash, where this Q and Q dash are prime numbers which are less than or equal to P. And the first 23 odd primes are 3, 5, etc. up to 89 are all cluster primes. Now, the definition of prime gap, it is known if there are infinitely many cluster primes, but Blacksmith shows that for every positive integer s, there is a bound x naught says that if x greater than or equal to x naught, pi c of x less than x by log x raised to s, where pi c of x is the number of cluster primes not exceeding x. The prime gap preceding a cluster prime is always 6 or less. If you consider a set of prime numbers, the prime gap can be even numbers, but for cluster prime, the prime gap is always less than or equal to 6. It is a property of cluster prime. If Pn denote the nth prime, if Pn minus 1 is greater than or equal to 8, then Pn minus 9 cannot be expressed as the difference of two primes not exceeding Pn. Therefore, Pn is not a cluster prime. I have listed all the cluster primes between 1 to 100. After 89, the next cluster prime was, next prime was having difference 8, but we can show that it is not a cluster prime. Now, one example is 11 is a cluster prime since every number less than P minus 2, that is 11 minus 2, they are 2, 4, 6, and 8. They can be written as the difference of two primes less than or equal to 11, that is 5 minus 3, 7 minus 3 equal to 4, 11 minus 5 equal to 6, 11 minus 3 equal to 8. And my research objective was to find the solution of the Diaphantine equation P raised to x plus Q raised to y equal to z square, where this P and Q are taken as the cluster prime with prime gap is equal to 6, where x, y, z are integers. Here we give the notation Q is equal to P plus 6, and we shall use the notation P plus 6 is equal to capital P. And the first theorem, if the power of P and Q are even integers, that is when capital N less than or equal to 0, small n greater than or equal to 1, m greater than or equal to 1 be integers, And if the prime number is of the form 6n plus 5, then for all values of p, n, m, the equation p raised to 2n plus p raised to 2m equal to z square has no solution. When we take the prime number as of the form 6n plus 5, p square is of the form 4a plus 1. And if you raise the power to p raised to 2n, then we can see that that number is of the form 4a plus 1. And if you take p raised to 2n plus 2p raised to 2m, we will get 4a plus 1 plus 4b plus 1. That is equal to 2 times an odd number. This will not be a perfect square. Therefore, if the power of p and capital P are of even integers, there will be no solution. Next case is when x is, if x or y is of odd integer. In this case, capital P is equal to power of capital P equals to 2t plus 1. That is an odd number. The power of small p is an even integer. In that case, we are getting a unique solution for small p equal to 5 and capital P equal to 11, where n equal to 1, t equal to 0. 5 square plus 11 square equal to 36. That is equal to 6 square. Next theorem. If P and capital P are two cluster primes with gap 6, then the equation P raised to x plus capital P raised to y equal to z square has exactly 7 solutions when x equal to 1 and y equal to 1 below 3 lakhs. With x equal to 1, y is equal to 1, we will get P raised to x plus capital P raised to y as small p plus 6, that is equal to an even integer, and z square is equal to an even integer means z is even. By solving, we are getting the solution for p as 18 into 5a plus 3 whole square plus 12 into 5a plus 3 minus 1, and z equal to 2 into 3 times 5a plus 3 plus 1 as the first equation. Similarly, we get another solution as 2. By giving values for a and b, we are getting these solutions, these set of solutions. When a equal to 3, 13, 14, we are getting 3 solutions. And for b equal to 0, 7, 18, 21, 4 solutions. Totally less than 3 lakhs, we are getting 7 plus 1, 8 solutions. Then further insight into cluster primes using programming approach. First, I try with Excel programming, and if you are carrying the numbers up to 100 or 1000, we can solve the equation using Excel programming. And this task becomes impossible if we need to extend 1000 or 1 lakh to find cluster prime pairs satisfying the equation p raised to x plus q raised to y equal to z square. We use programming techniques in Excel, VBA, and Java to do this analysis. And using Visual Basic application, first I try to find the cluster prime. In the Excel sheet, the column A, we put the number 17, and applying a programming, we find the set of numbers less than p minus 2, set of even integers less than p minus 2, and get the difference as the difference of 2 primes. These set of numbers are expressed as the difference of 2 primes. This is an example for a cluster prime, and this is an example for a non-cluster prime, because 97 is not a cluster prime. After 89, the next prime number is 97, whose difference is 8, and 97 minus 8 gives a number which cannot be expressed as the difference of 2 primes. And this is the procedure using Visual Basic application in Excel. And the Java solution, using Java solution, we are getting less than 3 lakh, the 7 solutions for p plus capital P is equal to z square. This is the Java output, and these are the references. Okay, thank you.
Thank you, ma'am. Any queries from the participants? Okay, thank you. So we move on to the next presentation, CP27. Ms. Radhika Das.
Yes, ma'am. Can you hear me?
Yes, you are audible. Please share your presentation.
Ma'am, the other participant is still sharing now, so we have to wait for some time.
Ms. Bindu, can you please stop sharing? Okay, now you can share the presentation.
Okay, ma'am. Ma'am, can you see my slide?
Yes, the presentation is visible. Your time starts now.
Okay. Good afternoon, everyone. Structure of different categories of Diaphantine tree tuples concerning the 2J centered polygonal numbers. Diaphantine M tuple. A set of M positive integers A1, A2, etc. Am is called a Diaphantine M tuple if Ai into Aj plus 1 is a perfect square for all 1 less than or equal to I less than J less than M. Few examples. For the first quadruple was founded by Fermat. The example is given by 1, 3, 8, 120. Euler, a generalization for this is given, that is A plus B. One second. A plus B plus 2R, 4 times R plus A, R plus B, where AB plus 1 is equal to R square. If A is equal to 1 and B is equal to 3, if you substitute A is equal to 1 and B is equal to 3 in this equation, we get a generalized, in this generalization formula, we get a Fermat's quadruple. Property D of N. A set of M positive integers A1, A2, etc. Am is called a Diaphantine M tuple if Ai into Aj plus N is a perfect square for all 1 less than or equal to I less than J less than M of size M and where N can be any positive or negative integer. Centered polygonal number. The centered polygonal numbers are a class of series of figure-8 numbers, each formed by a central dot surrounded by a polygonal layer of dots with constant number sides. Each side of a polygonal layer contains one more dot than each side in the previous layer. So starting from the second polygonal layer, each layer of a centered k-gonal number contains k more dots than the previous layer. These are few examples of a centered polygonal numbers. The first one shows the centered triangular number. The next is the centered square number. And the last one, the centered pentagonal number. General formula. Each centered k-gonal numbers in the series is k times the previous triangular number plus 1. This can be formalized by the expression kn into n minus 1 by 2 plus 1, where n is the series rank starting with 0 for the initial 1. These series consist of the centered triangular number, that is the series is 1, 4, 10, 19, 31, etc. The centered square numbers 1, 5, 13, 25, etc. The research objective. In my paper, an extension of a Diaphantine triple concerning the 2J3 centered polygonal numbers are evaluated using different centered polygonal numbers like centered decagonal numbers, centered dodecagonal numbers, and centered tetradecagonal number. Construction of a Diaphantine 3 tuple. First, we consider the Diaphantine 3 tuple 2J centered decagonal numbers. The general formula for the centered decagonal number is defined as CDN is equal to 5n into n minus 1 plus 1, where n belongs to the set of natural numbers. The sequence of the 2J3 centered decagonal numbers obtained from the centered decagonal sequence pointed by 22J plus 3, 62J plus 3, 123J plus 93, etc. The relation between the elements of 2J 2J3 center decagonal sequence is given by CDN is equal to 2J CDN plus 1 plus 3 CDN, where n greater than or equal to 1, given that CD1 is equal to 1 and CD2 is equal to 11. Consider the two tuple lambda 11 gamma 11 center decagonal numbers such that lambda 11 into gamma 11 added with a polynomial is a square. Lambda 11 is equal to 10j plus 15 n square plus 10j minus 15 into n plus 2j plus 3. Gamma 11 is equal to 10j plus 15 n square plus 10j plus 25 n plus 22j plus 3. So if you notice here that when lambda 11 into gamma 11 plus n1 is equal to a perfect square, where n1 is equal to minus 160j plus 160 n square plus 240j minus 80 into n plus 100j square minus 192j plus 60. Therefore, the pair lambda 11 gamma 11 is a Diaphantine two tuple with a distinguished property d of n1. To extend the two tuple into a three tuple, I consider delta 11 as the third element in the above pair. So it satisfies the following system of equation, that is lambda 11 into delta 11 plus n1 is equal to a square, gamma 11 into delta 11 plus n1 is equal to b square. From equation number 1 and 2, I obtain the result number 3. With a new transformation, I obtain a is equal to eta plus lambda 11k and b is equal to eta plus gamma 11k. Substitute equation number 4 in 3. So I obtain eta square as lambda 11 gamma 11 k square plus n1. Substitute k and k as 1. So I obtain eta is equal to 10j plus 15 n square plus 10j plus 5 n plus 12j minus 5. I mark that as equation number 6. So from here, I compute the value of a by substituting in equation number 6 and putting k is equal to 1 in equation number 4, and I obtain the result delta 11. Therefore, lambda 11 gamma 11 delta number 11 is implicated as a Diaphantine 3 tuple with the property d of n1. Similarly, I obtain delta 12 and delta 13 by computing the tuples lambda 11 delta 11 and lambda 11 delta 12. You can see delta 12 and delta 13 in the slide. Here are few triples by choosing n and j as listed. It is shown in the slide. Similarly, by using the same procedure, by taking the tuples gamma 11 delta 11, I obtain theta 12, gamma 11 theta 12, I obtain theta 13, gamma 11 theta 13, I obtain theta 14. Again, I have illustrated few results here. Now the Diaphantine 3 tuples using the center door decagonal number. So I have a general formula here. CDDN is equal to 6n into n minus 1 plus 1. I consider the sequence 26j plus 3, 74j plus 39, 146j plus 111. The relation is obtained by CDDN is equal to 2j CDDN plus 1 plus 3 CDDN, where n greater than or equal to 1, where given that CDD1 is equal to 1 and CDD2 is equal to 30. Consider the two tuples lambda 21 and lambda gamma 21 containing the 2j centered decagonal numbers by multiplying lambda 21 into gamma 21 and add by a polynomial to get a square. And I obtain the result lambda 21 into gamma 21 plus n2 is equal to a perfect square, where n2 is equal to 12j square minus 180j plus 27. So I obtain lambda 21 and gamma 21 as a Diaphantine 2 tuple with distinguishing property d of n2. Applying the same procedure as told before in the slide, from lambda 21 and gamma 21, I obtain delta 21, gamma 21 and delta 21, I obtain delta 22, lambda 21 and delta 22, I obtain delta t3, satisfying the property of d of n2. Now, similarly, using the above mentioned procedure, from gamma 21 and delta 21, I obtain theta 22, gamma 21 and theta 22, I obtain theta 23, and from gamma 21 and theta 23, I obtain theta 24. Few statistical values are stated here as the choice of n and j. Now, Diaphantine 3 tuples with using the centered tetradecagonal numbers. The general formula is given by CTTDN is equal to 7n into n minus 1 plus 1, The sequence that I choose is 30J plus 3, 86J plus 45, 170J plus 29, etc. The relation is given by CTDN is equal to 2J CTDN plus 1 plus 3 CTDN, where n greater than or equal to 1, CTD1 is equal to 1 and CTD2 is equal to 15. Using the similar procedure, lambda 31 into gamma 31 plus n3 gives a perfect square where n3 is not here. So you can say that lambda 31, gamma 31 is a two tuple with distinguishing property d of n3. From lambda 31 and gamma 31, I obtain delta 31, lambda 31 and delta 31, I obtain delta 32, lambda 31 and delta 32, I obtain delta 33. Few illustrations are here. Similarly, we can again find theta 32, theta 33, and theta 34 here. In order to conclude, I here used in this paper multiples of Diaphantine triples concerning the 2J3 centered polygonal numbers, which are evaluated using the centered polygonal numbers like centered tetrahedral numbers, dodecagonal numbers, and decagonal numbers. These are my references. Thank you.
Thank you, ma'am. Any queries from the participants? Okay. So, contributory paper presentation session 2 is over. Next, we have at 1:30 p.m. we will have talk 6 by Narayan and IIT Chennai on probabilistic methods in graph theory. So, see you all at 1:30 p.m. Thank you.